is this value, that is K, this is Kx. And the Cx dot is a C omega x cosine omega t minus theta plus 90-degree difference. So I have to rotate this 90 degrees. Right? Okay, I have a cosine theta. And then if I have a cosine theta plus 90 degree, meaning that I am rotating this 90 degree. So this is what? C omega x. And x double dot P M is this. That is M omega square x. Okay, now I have a very interesting diagram that essentially gives me all the physical observations I had using this graph. Often we call this phasor. The phasor is commonly used in optics, electromagnetics, acoustics, vibration, everywhere. Now, you have two choices. You can either use a phasor to understand the physics behind the vibration, or you can just use the mathematical formula which I used, add this magnitude and phase graph. Or you may use both to have a splendid picture that is associated with vibration. Now let's see. Beautiful geometrical relation. And this is a triangle that has 90 degrees over here. So I can say F0 square has to be equal to C square omega square x square plus, what is this? What is this? This length is kx minus m omega square x. The square. Okay? That give us this. You can walk on and you can make sure. If I am wrong, then I owe you guys to give you awareness. And what about the face? This. The face. Sorry, I made a mistake. Actually, small mistake. This is right. Okay. Terrible mistake. The phase is arctangent of this one over this one. What is this? C omega x divided by this one minus this one. Right? That is very similar with omega n square minus omega 2z omega n. Okay? Now, highlight of seeing this picture. And omega is getting smaller and smaller. What happened? Omega square shrink very rapidly. This one phase length, omega shrink, but omega n square shrink very rapidly, right? Okay? Then the phase angle approach to zero. Right? Then I demonstrated using the famous so omega is smaller than natural frequency. The phase is zero, meaning that I'm moving this mass with same phase angle of displacement. Meaning, another meaning is I only feel stiffness. I do not feel M or C. Okay, if I increase the omega, then what will happen? Still this is constant, but omega go up. Okay? Then omega square increase like this. Therefore, the phase goes to what? High, 180 degrees. So I can see more realistically that when I go to high frequency, the phase between excitation frequency omega, right? The phase between excitation and response go to pi, 180 difference. Right? What does it mean by 180 difference phase? The phase difference. Can you demonstrate the phase difference? I attempted for a long time. It's not easy. But think about it. Or when, for example, if I make a phasor like this, that means kx equal to m omega square x. That means k equal m omega square. That means omega square equal to k over m. That means excitation frequency is exactly the same as the natural frequency. In this case, the phasor forms this geometry. Meaning that many things. At natural frequency, the force is in phase with the velocity. The natural frequency. That means that what I'm explaining now, you never find this kind of explanation in any vibration. Natural frequency. This is like, I can adjust my stiffness. The reason why I'm using this very root, this kind of material that you can get anywhere, because I want to emphasize that you can do the experiment anywhere. Particularly we can do the experiment from here, laboratory.